Hello everyone. So today is my second lecture, and yesterday I promised you that I would try to make things more concrete, more formal. And let me start just by recapitulating some of the things that I discussed yesterday, and also some of the questions that some people asked me that I think it's nice to come back to this. So basically, in this first lecture, I talked about this model-independent way of describing thermodynamic transformations. The idea was very simple. We have a system of dimension d, very far from equilibrium. We have access to a thermal bath at some inverse temperature beta. The only constraint that we put is that this bath is prepared in a thermal Gibbs state, which I'm denoting by gamma. Then I assume that the system is closed, so they evolve unitarily. And I actually add a constraint this unitary to be energy preserving. And this defines me my thermal operations, which are just CPTP maps with two properties. The first property is that it's time translation covariant. And the second property is that it's Gibbs preserving. And as I said, the first property is somewhat like a manifestation of the first law of thermodynamics, and the second property, being Gibbs preserving, is a manifestation of the second law of thermodynamics. And then after this, I try to convince you that the question that we would like to answer, the fundamental question, and the question that it's what I would like to discuss in all these three lectures is, given two pair of states, rho and sigma, whether there exists a thermal operation between these two subsystems. And as I said, this is a very hard question to answer, specifically because we are allowing an arbitrarily thermal bath that we are very agnostic about. We allow any energy preserving unitary coupling then. And if I really want to know whether this rho can be transformed into sigma, in principle I would have to check for all these possible constructions that I might have. And this is a very hard problem. So then what I proposed then was like, okay, so let's look at a very simple case that we can give some answers. Those answers I presented today, which is the case in which the states that I'm dealing with are diagonal in the energy eigenbasis. So they're called energy incoherent states. So this means that, for example, I can span them in this way. So here are my eigenstates, and those probabilities which appears here I can collect into a vector of populations. It is a probability vector. And then basically all my description now can be brought into probability vectors evolving under stochastic matrix, which preserves the Gibbs state. So Gibbs preserving matrices. And then I finished this class by talking about this very important theorem from 2013, where they showed that there exists a thermal operation mapping rho into sigma for energy incoherent states, if and only if there is a stochastic matrix mapping P into Q, with the constraint that this stochastic matrix here preserves the Gibbs state. So it's this, just let me make a, this is also Gibbs preserving. So if I take a thermal state, I map this back to a thermal state, right? And well, just friendly recall, stochastic matrices, all its entries are non-negative. Let me denote by this. Bigger font, perfect. So stochastic matrices, all their entries, which I would just denote like this, just notation, are non-negative. And then if you sum the columns, because of probability conservation, this goes to 1. Great, so we can really simplify the problem that we want to solve, because now the idea is to look at, as I said, probability vectors evolving under Gibbs preserving stochastic matrices. So now also another, so basically, so the two questions that I would like to discuss today is this one. So suppose that you give me two energy incoherent states represented by their vector of populations P and Q, whether there exists a Gibbs preserving matrix mapping P into Q. Because if this is true, we know that we can construct a thermal operation mapping rho into sigma. And the second question is a bit more general, which has to do with this idea of thermal cones that yesterday some people were confused about it, which is the following. Okay, suppose now that I have my initial state, I have this bath at this inverse temperature beta. Can I construct the set of states that I can achieve from this initial distribution? So instead of looking at pairs of states, I'm looking at a specific state to a set, or the set of possible states, right? And the way that I denoted this was using this representation of light cone, which I think it was a bit confusing for some of you. It's just like a nice way of representing. But the idea is precisely this one. So we assume that we start with some rho. This rho is energy incoherent. And now we are asking for all these sets that we can achieve under thermal operations. So basically, what I mean here, and I will denote this by T plus, is precisely all sigmas and other states that are achievable from this guy via Gibbs preserving stochastic matrices. And as I said, I will not present the solution of this problem, but we can make this problem a little bit more interesting by also asking what is the set of states that can achieve this initial distribution if they are also in contact with this thermal bath at temperature beta, 1 over beta. And this, I call it PAS, thermal cone. And one of the things that I basically motivate yesterday, and today will be clear, is that this is not a total order, meaning that there will be states which are neither in the past nor in the future, so they lie here outside of this thermal light cone, and this is called incomparable set. So basically, it means that there are states which cannot be transformed into yours, and vice versa. You cannot construct a thermal operation between them. But as I said, this is just a nice analogy with light cone, and we will see an explicit example on how to construct those things today. And also, why this is important? Because basically, if we know how to construct those things, we know precisely everything that we can do with this initial configuration of the system. So let's suppose that we want to prepare some nice qubits for quantum computing. We want to reset them. And then we have access to things that I will later mention called elementary thermalizations or elementary thermal operations. Can we prepare the desired states having access to this? Well, in order to check if we can, we should just look at the future thermal cone of this state, okay? And also, yesterday, many people were confused by this terminology of future past. Future is just the set of states that you can evolve to. Past, the set of states that could evolve yours at that inverse temperature beta there. And also, this is very nice. It is something that I will skip, but these kinds that also shed light onto this very old problem in thermodynamics, which is the thermodynamic error of time, right? Because you could look at this thermodynamic error of time in terms of reachability under thermal process. Great. So that's very nice. And just like yesterday, after the class, I'll try to finish around 1 hour or 1 hour in each and stay here. And then we can discuss, we can go through those calculations all together. So let me start then by giving you a partial answer to this first question. And basically, from this moment now, I already saying sorry because I will present many different lemmas, theorems, but I will not prove them. Why is that so? Because many people already proved them. There are many good books about this, and all those things are basically matrix analysis. And I will recommend you good books that would do a much better job than myself here. So let's look at a very specific case, which thermodynamically speaking, it's a bit funny, but this specific case will allow us to construct the theory that we are aiming to. Let's look at the extreme case in which beta is equal to 0. So beta is equal to 0, infinite temperature. Infinite temperature, thermodynamic doesn't play a role, only information. But it's meaningful because from this I can derive theorems, try to generalize those theorems for when this temperature is not infinite. And then the most beautiful thing that you see is that those theorems which once hold for beta equals 0 will fail to hold. And this is very nice because then we can get some salary, some grant to try to generalize them and discover new physics. Great, so beta equals 0. So what does that mean? From that question that I put there, we wanted to ask whether there exists a stochastic matrix mapping P into Q, and that stochastic matrix has to preserve the thermal state. What is a thermal state? It's simply gamma E2 minus beta H over Z, but now beta is equal to 0, and this is simply identity over D. So in other words, if you think about distributions, uniform distributions are maximally mixed states. So basically, our problem then can be reframed in the following way. So I want to know whether there exists. Now I will put a 0 here because beta is equal to 0, whether there exists a stochastic matrix, which when acts on P gives me Q, and when it acts on this thermal state, that now I will change the notation just to make it distinguishable. I will denote this maximally mixed state or uniform state by eta. When it acts on eta, gives me eta back. And then the properties of this matrix, sorry for being redundant, is that this Ji is always larger than 0, those entries, and before we had that the columns, sum over J, sums to identity. Sorry, not identity, sums to 1. Well, now if we do some algebra, this is an exercise for you. If we take this condition, open up this equation here, we will learn that now this is stochastic matrix, their column will sum to 1, but not only the column, but also the rows. So this means that if I sum over I here, this will also go to 1. When this happens, this is a very well-known object in math. This is called bistochastic or doubly stochastic matrix. And the nicest thing is that now we can invoke many mathematical results to solve this question. Why is that so? Well, precisely because many of those things were already studied back to 50s and so on. And okay, that's good. So now, the first theorem that I will invoke, but before, let me just say that if you'd like to see the proofs of those theorems, there's this very beautiful book by Bhatia. It's called Matrix Analysis. Everything is very, very nice proven there in a very friendly way, but there's also this 1,000-page book by Marshall Hawkins about majorization, which is what I'm gonna talk today. So basically, the first theorem is the following. The first theorem is attributed to 3 mathematicians. I will put HLP, Hard, Littlewood, Polya. And there's a very funny story connecting these 3 people. I will not say now because it's on camera and so on, but it's some sort of gossip. If you'd like to know, you can come and then I can tell you. It's very funny. So basically, Hard, Littlewood, Polya theorem says that, well, there exists a bistochastic matrix mapping P into Q if and only if P majorizes Q. And now you can ask me, okay, what is majorization? Majorization, it's a way of comparing probability distributions relative to your uniform distribution. And in other words, you have a way, an algorithm to compute those things. It's very simple. I'm gonna define majorization now. But before defining majorization, what is very nice is that the solution of this problem now consists of checking d-1 linear inequalities. So it is kind of done, and this is very nice. Majorization appears in different facets of not only physics, but also economics and so on. So it is something extremely general. And probably you heard about this. If we think, for example, about, suppose that we have bipartite pre-entangled states and we ask whether we can transform a given bipartite state psi into phi under local operations and classical communication. Nielsen in, I think it was 1996 or 2001, I don't recall now, showed that the criteria boils down also to check majorization with respect to the Schmidt vectors. But there it is really nice because basically the majorization is the other way around, in the sense that there exists a bistochastic matrix mapping P into Q. There are Schmidt vectors if Q is majorized by Q. So in other words, if we think about entanglement and thermodynamics, what I call future in thermodynamics is the past of entanglement and vice versa. Okay? Sorry, this was not in the script. This is why this is a bit incoherent, but this is very, very nice. And this is just a way to say that majorization also play many different other roles in quantum information theory. Good. So how do we define majorization then? So let me think. Maybe I will go to the other side to be more democratic. Sorry, I will get my coffee as well. So let's assume that, let's start with the definition. Let me try to be coherent. So let's assume that we have two d-dimensional probability distributions, P and Q. So basically, let me just write P to be like P1, PD, Q the same, Q, Q1, QD. And let's also consider P and Q ordered in non-increasing order. So basically, I order these two probability distribution here in non-decreasing order. Okay, so like this. So we say that P majorizes Q and denotes by this nice symbol here. If we look at partial sums of I equal 1 to K, Py, K is larger than I equal to 1 to K Qi with K being 0 to D, for example. Okay, no, 1 to D. So basically what we are doing here is, let me read it again. We say that P majorizes Q if it's partial sum running from 1 to K, and K is just an index which goes from 1 to D. The probability vector P ordered in non-decreasing order is greater or equal to the probability vector Q ordered also in non-decreasing order. So basically what I'm saying here is that first we need to do the following. So we take P1, we ask if P1 is greater or equal to Q1, then for K equal to P1 plus P2 is greater or equal to Q1 plus Q2, and so on and so forth, just 1 larger or equal to 1, which is trivial. Okay? Yeah? Yeah. Yes. Okay. It's not necessarily, you can always append some zeros there, but for the things that I will say, yes, but yeah, not necessary. Yeah. Thank you for the question. Let's see an example. I know that this is very simple and trivial, but let's just take an example. Suppose that P is 0.7, 0.2, 0.1. And let's suppose that Q is 0.5, 0.3, 0.2, okay? So basically now, if we want to know if P majorizes Q, I just need to apply this. So let me make it here. So 0.7. So they are already ordering non-decreasing order. So let me make more interesting and actually put 0.2 here, 0.5, 0.3. Yeah, good. So this vector is already ordered in non-decreasing order. So ordering Q means that this 0.5 comes here, 0.2 goes there, and 0.3 go here. And now we compare entry-wise, right? So 0.7 larger than 0.5. Now 0.7 plus 0.2 is 0.9, larger than 0.8, and then 1 equal to 1. So basically, from this example, very simple, we see that P majorizes Q. And if P majorizes Q, we know from this theorem that there exists a bistochastic matrix mapping P into Q. But as I said yesterday, this thermodynamic ordering is not total, but partial. So it means that it might exist some vector R that neither majorizes P nor is majorized by it. So for example, R could be 0.6, 0.4, and 0. Why? Well, simply because first, if we compare the first entry, we pass on the test, 0.7 is larger than 0.6, that's nice. But then in the second partial sum, 0.7 plus 0.2 is 0.9, and this is 1. So basically we fail in the second inequality. So P doesn't majorize Q, nor Q majorizes P. And so not Q, sorry, R. And this is precisely one case that this vector here is in the incomparable region of P, right? And Q is in the future of P. Why? Because basically there exists a stochastic matrix, a bistochastic matrix mapping P into Q. So Q lies in the future of Q, but there's no bistochastic matrix mapping P into R or vice versa. So this is incomparable by my definition. And if we think about a thermal process at beta equals 0, so then I wouldn't be able to construct a thermal process in that way that I showed there here when I defined thermal operations at the level of maps. Also, this is very relevant because that set of operation, it's known in the literature as noisy operation, because basically you are replacing thermal state by maximally mixed state, you are introducing some noise. And there's a very nice review from 2017, which basically discussed this set of operations in a very nice way. It's on the notes. Oh yes, because there is a theorem now which says that basically, maybe this is not the way, because okay, I will say the theorem later, but well, did you remember that yesterday I said about those monotones and so on? For this type of things, Shannon entropy is a monotone, and then there's this theorem here which says that, well, if this is, okay, I didn't plan to write down this theorem, but let me see if I remember, more or less. So it is sure convex or sure concave, which says that if P majorizes Q, so then this implies that there's a function f which acts on P, which is greater or equal f of Q. And if this is true, this is called sure convex. Concave is precisely the other way around. Yes. Yes, exactly. Yes. And you can generalize this to this so-called alpha any entropies, where this alpha is any parameter in the real line, so you have an infinite amount of guys there. I will talk about this tomorrow, because then I will look at thermodynamic transformations, and this has this very nice interpretation with this family of second laws that you have. But here you can see, right, that yesterday, by the way, there was a very nice question where yesterday I wrote a monotone for thermodynamics, which was the relative entropy between your state and your thermal state. And then later on, we interpreted this as the maximum amount of work that you can extract from an out of equilibrium system while in contact with a thermal bath, right? And then the very nice question was if this is if this is necessary and sufficient to characterize thermodynamic transformations. Unfortunately or fortunately, the answer is no. It's precisely because we are dealing with a partial order and not total order. So why you can see here, because basically it might be that you can construct a function in which if you assign here, this function will be greater than r, and then in principle you could be led to think that you can transform P to R, but this is not the case. Like the strong case here is majorization. And then you can say, what if you have all this whole family? Well, then it's very specific. It's, you know that it's necessary, but not sufficient. Mm-hmm. Well, there's a trick that I will also talk about this tomorrow, which is when you bring an auxiliary system, which allows you to perform this transformation with the condition that you bring its state back unchanged. So in other words, this system acts as a catalyst. You don't consume its resource, but you use other auxiliary degrees of freedom to allow you to achieve this transformation. And but then, okay, connecting to your question, but then when you bring this system and then you allow the system to create correlations with the constraint that its marginal is precisely the same, then you kind of go under the direction that you're saying, that you add one constraint more and then you have... Yes. Well, I'm not sure if this was clear, but just since we're just chatting, so what I'm saying is that, well, there are cases in this, when I write my theory in terms of partial ordering and so on, majorization, that you cannot transform, let's say, A into B, but then you can always bring a system C, such that now this transformation becomes possible. And then this was first discussed by Jonathan and Plenio in 1999, I think. And basically there they were looking at the case of entanglement manipulation under local operations and classical communication. And it was precisely this case that you couldn't transform, but then by bringing this auxiliary system, which is a catalyst, you could perform this transformation. And there are many different ways of making this very interesting. For example, here I demand that the output state is a product state. But we could also relax this and allow for correlations, such that the output state now it's not a product state, it's some correlated state. But then if I look at the marginal for this catalyst, it is precisely the same state. In the second situation, we have this idea of correlated catalysis, which is a very hot topic in the moment. And basically, with this notion of correlated catalysis, we can more or less nicely formulate this family of second laws. Okay, good. Yes, sorry for those comments that that I make out of the blue. It's just that one thing leads me to another. So let me just come back to what we were saying. So basically, then we kind of answered the first question. Okay. Yeah. Mm-hmm. Oh, it's fine as long as if you trace out B and look at the state of the catalyst, you have the same state. So the marginal state is unchanged, but the correlated state, but you allow some correlation. It's a correlated state. It's not like a product thing like here. Yes, and correlated catalysis is much more powerful than compared to the product version, yes. Yeah. Yes, this idea of catalysis, maybe I will talk about this, because basically catalysis is a very powerful tool. and which first appeared, well, okay, catalysis is an old idea of chemistry, right? Where you use chemical compounds to speed up chemical reactions or allow you to perform some otherwise impossible transformation without degrading its resource. But then Plenio and Jonathan made this very nice connection with entanglement theory, and then people start applying to other resource theories, such as coherence, such as thermodynamics, and so on. And then right now, catalysis is a very powerful thing, and it goes beyond of just being a mere abstraction. For instance, you can use correlated catalysis to generate non-classical states of light in this Jaynes-Cummins model. This is really nice. Might mention about this tomorrow. Okay, good. So basically, let me come back then to what we were discussing. So basically, the question that I pose, whether there exists a bistochastic matrix mapping P into Q, the answer is provided by looking at this majorization condition. Majorization is very simple to compute, even if your system has, like, it's very, very, very high dimension, like you just check inequalities and so on and so forth. There's a very nice way also of looking at this majorization in terms of a more geometrical thing, object. This is called Lorentz curves or majorization curves. And basically, majorization curves you define in the following way. So majorization curves, basically, it's a piecewise linear curve where you take, let's say, so you have P, you have Q, and then you basically join 0, 0 with points like, those are coordinates with, here it goes 1 to k. Here in the y-axis, I will put eta I will explain why. Here I will put 1k, py ordered in non-increasing order. So basically, it's a piecewise linear curve whose components are simply given by this. And this eta here is basically my maximally mixed state, my uniform distribution. In principle, if you look at the literature, they will put a k here. So you go from 1 to d. Here I'm putting like eta because it's just a renormalization of the x-axis. Nothing changes. And this allows me to connect nicely with the finite temperature case. So for instance, so what I'm saying is that basically this Lorentz curve or majorization curve is obtained by joining those things. So for example, here you have eta 1. Eta 1 is 1 over d, right? And here you put like P1 ordered in on increasing order, and then you join this. And now here you would have eta 1 plus eta 2, and then here you have like P1 plus P2, and then you create this curve here. Like those are the elbows defined by this, and then you have this curve, okay? So this is called majorization curve, and it's just a graphical way of looking at the majorization relation, right? Because what I'm doing is precisely plotting this set of inequalities. And basically, I will denote this curve by f of p, put some x here, and it is trivial to see that p majorizes q if and only if f of p is always above f of q. So f of q would be something like this. Right? So for the example that we are considering, P equal 0.7, 0.2, 0.1, Q 0.5, 0.3, 0.2. So this is already order. So basically 0.7 would go here, then 0.9 would go here, and 1 would go here. So you see. Yeah? So far so good? Yes, very simple, right? Yes, very simple answer for a very hard problem. Great. Basically now, so we kind of answered the first question for beta equals 0. So I will put some check here. Now I would like to discuss something about the control. The control in the sense that if we look back at this picture over here, so basically what we have is that, so you have your density operator, your system, you couple with this BEF, and then you perform this energy preserving unitary, right? And basically you don't know how this energy preserving unitary acts on your system. So for example, we could imagine that you have your system with its energy levels depicted by those lines. You have this big unitary U here, transforming this in this way, right? Well, sometimes it's desired, just like in quantum computing, when you break down this unitary into small pieces. So basically in elementary operations. What elementary means now is that, well, you act on non-trivially in two energy levels and identity everywhere. Meaning that whether you can break this as, or if this unitary is equivalent as writing something like this. First you act in the first and second energy level, then you act in the third and fourth, and then maybe you act in the this and this guy here. Whether this is possible. Because if this is possible, you could basically engineer like optimal thermalizations of your system, just coupling specific energy levels with the BEF. If you assume that you have control under the degrees of freedom of this BEF, right? But what I'm claiming so far is that, well, my BEF could be in principle everything. It could be a qubit, a qubit. The only assumption is that it's prepared in a thermal state. No. Here is just like a very sloppy sketch that, yeah, it should be system and BEF, but here's just a sloppy sketch saying that, yeah, energy levels of the system. Yeah, I mean, I should do this better, but it is just like a bad graphical thing that came to my mind right now, and then I wrote. But the idea is this, whether you can break down this big unitary there into smaller pieces. Because the faith is that if you can do this, then in principle we could engineer nice process or make it simpler for experimentalists. Well, we are very lucky because at beta equals 0, this question was already answered more than 50 years ago by the same guy that introduced this notion of majorization, the Moorhead. And now I will bombard you with another theorem, though it's pretty simple. So theorem number 2, now it's Moorhead, Hard, Littlewood, Polya. So basically what this theorem says to us is that if there exists a bistochastic matrix mapping P into Q, we can always decompose this bistochastic matrix as a finite set of T transforms. I will define what is T transforms. So this, let's say, I know this, let me put this. Should have my notes now, but I don't have it. P. Yes, okay, it's a weird notation, but yes. So basically what I'm saying is that, yeah, let me define. So this is a T transform. And a T transform is just a convex combination between doing nothing plus a swap operation. I will denote this by I1, J1. So basically, this swap operation, as Wilviga mentioned in the first lecture, acts non-trivially in two levels and identity everywhere. Right? This is just a transposition. And this is very nice, because basically what this is telling us, if we translate to the language of maps, is that at beta equals 0, I can break down this unitary in smaller pieces. For example, so suppose that I have my initial state 0.7, 0.2, 0.1. I have my Q, which is 0.5, 0.3, 0.2. Now I can try to construct, we know that we can transform P into Q, and then we can try to construct the stochastic matrix which does this. And well, in this case it's pretty simple because we have a 3-level system and we have plenty of conditions to write down possible candidates for that stochastic matrix. It's not unique, this transformation actually might be that there are many of them, but we can construct this following one, which is simple. So put 2/3, 1/3 here, 0, 1/3, 0, now 2/3, 0, 0, 1. So let's check. This is a candidate of a stochastic matrix. So the rows sums to 1, the columns also sums to 1. So it's a stochastic matrix. And now if I take this guy here, apply on P, you can do the calculation, you see that you can get Q, okay? And basically what this theorem is telling us is that, okay, we are able by this theorem to break down this into smaller pieces. And now comes the hard part. 2/3, 1/3, 0, 1/3, 0, 2/3, 0, 0, 1. Oop. So this is like this. Thirds, and this will be 1, 0, 0, 0, 0. Can I do like this? Wait. Or this here. Okay, better to get the notes. I was almost right. It's 1, 1, 0, 0, 0. This is 1, 0, 1, 0. Ah, that's true. Thank you. Great. So basically, yes, so we can take this stochastic matrix and break down into this product. Here we can see that we have a transposition here between energy levels 2 and 3. So this is precisely P2, 3 plus identity everywhere except 2 and 3. The identity is here. And this is precisely, let me make a, this will be 2/3, 1/3 P13 plus 2/3 identity, which is a T-transform. So I flip a coin. With this probability, I don't do anything. With this probability, I do a swap between energy levels 1 and 3. I will do this now. Yeah. So yes, so the next theorem is the following. So we are in very good hands here because we not only answered our main question, whether there exists a stochastic matrix mapping P into Q, but we were also showed that at this perspective of quantum control, we can also break down this transformation to be a product of, not a product, a sequence of elementary stuff. Elementary here with this notion that I act non-trivially only in 2 energy levels and identity everywhere. So now I would like to come to the second question, which is this idea of thermal cones. What is the set of states that you can achieve if you are allowed to apply stochastic matrices? And as Richard said, there is this very beautiful theorem. Let me now take this. So now my question was how to characterize this future thermal cone of P, right? What is the set of states that we can achieve if we start in P when the temperature is infinity? Well, there's a very beautiful theorem, which is the Birkhoff theorem, just put B, which says that the set of B stochastic matrix forms a convex set, and the extreme points of this convex set is permutation matrices. So in other words, you take your favorite B stochastic matrix, you can always write it as a convex combination between permutation matrices. Okay, so let me just write this as a convex set. Extreme points, permutation matrices. And those permutation matrices, they are B stochastic, so they can be broken down using this Moorhead-Hardy-Littlewood-Polya theorem into T-transforms. And I will just do one thing more, which is simply a corollary of the Birkhoff theorem. And basically, this corollary will allow us to characterize the future cone of this initial state P. Because if we now take Birkhoff theorem plus Hardy-Littlewood-Polya theorem, which is precisely this, this acting P is equal to Q, if and only if P majorizes Q. If I combine these two things here, then we can conclude that the future thermal cone of P, or the set of states here, is the convex suit of permutation matrices applying on P. Or this. Yes. Okay. So let's see an example, because this is actually very simple. It might sound hard at first glance, but actually it is not hard. So here, let's do the example here. So the same case that I keep looking at, 0.7, 0.2, 0.1, so a three-level system. And as I put it there, the space of states is the probability simplex, right? So just let me draw the probability simplex here. So here I have 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay? Let me just do something which will facilitate my life, which I divided this probability simplex into 6 equal parts. We call this bivial chambers. They are symmetric and permutations. So for my state, this coordinates 0.7, 0.2, 0.1, we are here. And then basically what this theorem is telling me is that now extreme points of this future thermal cone are permutations of these vectors. So I can come here. So there are 6 of them. And this region here is the future thermal cone of P. Not thermal, sorry, future cone of P. So let's interpret this with more care. So here's our initial state P. Here is like a permutation, a swap of one of the levels. So this is 0.7, 0.1, 0.2. This is precisely 0.2, 0.1, 0.7, and so on and so forth. What is the statement of this corollary is that we know that the set of states lying here are majorized by your initial distribution. So any state living here, you can transform using a stochastic matrix, right? And basically, let me just zoom in this a bit more. Let me see what I did here. Yeah, this can be written as okay. So here I have my P. Here I have a P2, 3, P, FP, 1, 3, P, 2, 3, P, P, 1, 3, P, P13, P12P, P12P. Nice. So basically, yes. So here I just wrote those extreme points, which are permutations of my initial vector, using this idea that I'm decomposing them as product of transpositions or concatenations of them, like products of them. And this is really nice because, well, despite the fact that we are looking at beta equals 0, we will generalize this for finite beta, but this gives us ways of engineering stuff in the sense that, look, if you tell me in my lab, I have this quantum state, I have access to those other states that I can treat as a BEF, what is everything that I can do using these ideas of energy preserving unitaries, thermal operations? So everything that you need to do, that you can do, lives here, right? And since we are deriving this under minimal assumptions, any model that you might take, even your favorite one, you'll be upper bound by what you can do here. So this is like a fundamental limitation on what you can do with your system. And you can use this for a bunch of nice applications. For example, imagine that you want to cool your system. Then let's say that you are here, and then you can find the optimal path to cooling your system according to some definition of cooling. And the same for other stuff like work and so on. I will expand more on this at the very beginning of the next lecture. So up to this point, is it okay? Because I think the first time that we look at this might be confusing. Yeah. Unfortunately, I will not construct the past cone, neither the majorization cone, but I can give you a gist on how they look like. So the proof behind the past cone and the incomparable cone is really, really cool, especially if you like majorization, if you like geometry. The proof is really, really nice. There's this very nice way of proving this, well, not proving, but there's this very nice characterization of the past cone where you relax the assumption that your probability distribution is a proper probability distribution. You go outside of the probability simplex, and when you project back, you get extreme points of this past. It's very nice, it's very intuitive, and this is not in the lecture notes, but it's in this PhD book that I wrote, that I mentioned yesterday. Let's see if this works. Okay. Oh, yes. So basically here, look, here we have beta equals 0. And okay, my mouse is strange. So here is beta equals 0. Here is our initial distribution. The set of states that we can achieve under bistochastic matrices is depicted in green. The set of states that can achieve our initial distribution is depicted in blue. And the set of states that I can't evolve, nor can evolve to mine, is depicted in red. Okay? And there's some nice geometric properties that I will not mention, such as like the future is convex, the past is not convex. But then if you look at those chambers, those Weyl chambers, which is like when you take your probability simplex, divide into equal parts, symmetric parts like this, the past is convex within this chamber. And there's another physics hidden here that unfortunately I will not be able to talk, which is like those chambers, they are not arbitrarily. Here I'm introducing this as mathematical stuff, but they connected with the nature of the process, if the process is Markovian or not. And this is really nice, because as we will see when we compute the Markovian thermal cone, we see that we will not be able to cross this border without paying a price. Which price? Memory. And then, okay, so this is valid for arbitrary dimension. So it is valid for, if your system has dimension 30, it is valid. Of course that you cannot visualize, but at least you have those extreme points, and you have nice methods to check and to construct those optimal algorithms for some application. And now I think it's the nicest part of my presentation, actually, because let's suppose that we have a 4-level system. Do you want to ask something first? No? So it is, okay, this is a bit tricky. It's well, I would say that it's not a cone. Let's say it's just like a terminology thing. When we see at the qubit case, you see something which resembles a cone, but yeah, no. But as I said, like, okay, this can go down now. So now it's the nicest part of my presentation, because basically, as I said, so we have a construction which is valid for arbitrary dimension and so on. And then when I got those things on my PhD for finite temperature, I got very hyped. I had those very nice animations on Mathematica. And then I did something which made our secretary extremely pissed, which was like they had just bought a 3D printer. And I wanted to print those thermal cones to see live. But then I didn't know how to use. So I ended up printing like lots of them. And this cost very much. But for a 4-level system with population, let's say, I don't remember. It was something like 0.7, 0.2, and 0.005, and 1 minus everything here. You have this thermal cone here. So as I said, only the future is convex. So I will open here, and then I will give you to you guys. So only the future is convex. The incomparable region, another fact about this, and very nice, is that it's disjoint pieces, which is this part. So the past is this white part here, and the future is precisely this very nice polytope here, this octahedron. So basically, what we are seeing is that if you start in this initial state here, it's a 4-level system, you can evolve to any other state which lies inside of this geometric shape here. States that you cannot map into bistochastic matrix nor can be mapped to yours are precisely these disjoint parts here, these gray parts. And states which are in the past is precisely what is left. That's nice. So I will give it to Rafael, and then you guys can see it, but please don't break it. And I also had one of for finite temperatures, but this one is really a puzzle, because we will see that when we go for finite temperatures, we break the symmetry, because there's a symmetry here that I'm not talking about. But yes, so you can pass to people and to see. Nice. So how is it going up to now? Is it okay? Are there questions, comments, or? Mm-hmm. Yeah. So what I'm gonna do now is to translate this to finite temperatures, and then when you see this, when you translate this to finite temperatures, the first thing that you realize is that you break the symmetry, because now your fixed point is not a maximally mixed state anymore, right? Which is here in the center of the probability simplex, but it's a thermal state, and we know that thermal state lives in this chamber, because in this chamber we have like P1 larger than P2 larger than P3, like this. So thermal states lie around this curve here. They are parameterized by this one family function of beta, right? So this means that now if we go from infinite temperature to finite temperature, meaning that we start decreasing the temperature, so thermal states will go along this path, and your future has to follow your future cone has to follow the thermal state, right? Because it's a fixed point. It is always contained in the future of any state. So you see that you break the symmetry when you do this.
I have a question concerning computer assisted constructions. Like a lot of these things, I guess, can you formulate this in your program?
Yes. Mm-hmm.
This is always the case. For example, over there, can I write it in your program that tells me to compose this?
So for thermal operations, no. For majorization, yes. For beta equals 0, yes. And I think this is okay, so since I'm already start discussing this finite temperature, so let me start with this, what Richard was saying, because basically, of course, that all this theory that I'm discussing here was done, well, in the 50s, in the 60s. We are just very lucky to have this physical question that we could use those tools that it was developed by mathematicians. But then the big question is when you look at finite temperatures. And then I think the naive thought is that, okay, everything that we do for finite will also hold. But they don't. especially because what I'm going to do next is to generalize this concept of majorization by another notion, a more general one called thermal majorization, which is a majorization relative to the thermal distribution. And then my next step then is to find this thermodynamic analog of that theorem of Hardy-Littlewood Polya. But then we say, okay, now this is very nice because if we have this theorem, we really can apply for, let's say, real life things and so on. But then this holds on the fact that we would be able to decompose this into a finite product. But for thermal operations, this is not possible, unfortunately. This is the breakdown. And yes. Yeah. Yes, exactly. Those dashed lines here. I don't know. Yes. So it's a question that I was very interested after finishing my PhD, but at some moment I realized that it was just like a more theoretical question that just myself was interested. So I stopped looking at this. But in order to construct, for example, these optimal thermodynamic paths using Markovian thermal process, you kind of use this idea here. Like you kind of look at what is the best you can do when you have to cross, but you want to do this in a memoryless way. Good. Yes, so for beta equals 0, yes, we can do this because in the end of the day, it boils down to swaps. For finite temperatures, not always. For some process, you can. Like, let's say, I'm giving you spoilers. We will generalize this for finite temperatures. There will be some extreme points, which are just like beta swaps. Instead of swaps, you have some Gibbs factor. Those you can construct. But then as you argue, there will be extreme points that cannot be written as products of beta swaps. But a nice thing that I will not talk is that it was a big problem that it was solved in 2022 by Camille and Matteo Lostaglio, that they showed that Markovian thermal process actually can be break down into a finite sequence of elementary thermalizations. And then in this paper, they basically answer the question, you give me your favorite open dynamics model, I can tell you how you can realize this with a universal set of elementary thermalizations. This is called, it's a long title. It's like fundamental laws of continuous thermomajorization. It's something like this. I can send it to you later, but if you put like Camille, if you write Matteo, Camille, continuous, you'll find it. Yeah. Okay, so how much time do I still have? Okay, so I have 22 minutes. I don't think 22 minutes is enough to go to the finite temperature case. So basically, then maybe I could just stay here and then you guys can come and ask me questions if you want. Or, okay? Yes, so just one thing, tomorrow will be much more interesting because when you put temperature, it's very, very nice and so implications. Thank you.